Greetings, we are from Sardar Patel Institute of Technology. We are Team EXO and our topic is exoskeleton legs. For a regular person, the process of movement of lower body limbs is dependent on three regions of the brain and one region of spinal cord. In the brain, the premotor cortex is responsible to prepare the body's muscle for the exact movements they will make. In other words, it will help you control your movements. The supplementary motor cortex is responsible for the planning of the movements like an algorithm, and the primary motor cortex, which is responsible to generate neural impulses that control the execution of the movement. The signals travel from the brain through the lumbar region in the back region of spine, which controls the movement. For a person suffering from a condition that restricts the movement of lower body, the main problem is the signals are not able to travel, that is, the neurons responsible are damaged. Now we know that the problem is the communication between the neurons and the muscles. Our solution to this problem is to take inputs from the surface of the primary motor cortex, then transmitting that signal to a microcontroller that will run a bipedal walking algorithm and control the movement of the legs through the motors that act as joints in the legs. Now let's talk about taking inputs from the brain. The firing of the neurons creates electrical impulses between the neurons in the synaptic gaps. These signals are captured using the principle of capacitive coupling, where an electrode with a conductive plate is used to send the impulse. This impulse is a very small signal, hence an instrumentation amplifier and a differential amplifier are connected to amplify the magnitude of the signal. A combination of these electrodes connected in a daisy chain connection will give us the signal to control the system. This signal is transmitted to the microcontroller. Here it is MSP432, which will initiate a bipedal walking algorithm. This MCU will take real-time inputs from the accelerometer and the gyroscope from the Boost XL sensor board and give feedback to the controlling of the MCU. The MCU will control the DC stepper motors with the help of high current DC stepper motor drivers. There are a total of 4 motors used to mirror the motion of a joint of a regular person. One motor on each hip joint and one motor on each knee joint. The calf in the human body acts as a shock absorber. Thus, we place a spring arrangement in the calf region of the exoskeleton legs. The entire suit will be tetherless, that is, the system will independently run on batteries. Here are the calculations for the batteries of the system. We are using lithium-ion batteries with a rating of 3.7 volts and 2200 milliamps per hour on each cell. Now our requirements are 48 volt DC to 170 volt DC with a current of 7 amperes. So if we use 14 cells in series, we get a total of 51.8 volts, and if we use those 14 cells in series with 4 sets in parallels, we get a total current rating of 8800 milliamps per hour. This will cause the motor to run for 1 hour 15 minutes at max load with a 56 cells, and the total weight of the battery system will be 0.033 kgs. Now we'll take a look at the customer validation. Here is a user who has a condition known as cerebral palsy.
Neurological condition called cerebral palsy. It affects my motor skills and reflexes.
How do you think our product would help you?
I have problems with my mobility, as in moving around, because the muscles in my legs are weaker than normal. So I think if your product can provide additional support for me while walking and could maybe provide a cushion to increase the time I can move around, I think that will be very helpful. As low as possible. I think if it charges sufficiently to us, it might help, because if I have to move around a lot, then